Hi everyone, so in today's video presentation, we're going to discuss a business case using the machine learning to predict the Ablone age. So basically, we want to replace the traditional human procedures. We want to boost up these kind of procedures. So we use machine learning to capture those features of Ablone and to predict the accurate age of it. So here is some basic procedure. We want to do some pre-processing, but after importing those libraries, we do some simple data analysis and data cleaning. So you can see here, so we introduce seven features as our independent variables, and only one, the ring, as the response variable, which are set as a target. So, and this one could be mentioned as that this is not the result we want to use as a response variable, because we have to add it by 1.5 to give the age in years. And you can see here there is a two data frame, and then we do some experimentary data analysis. So you can see here we do some checking on the missing value and also the duplicates, and checking on the unique values in each features. Since the infant have no specific gender, so we have three type of age as the unique values. And then you can see here, so after we do some simple observation, we draw some plots to better understand the data. We include some histogram, box plot, scatter plot, etc. You can see here there is very strong summaries about what should we take a look on. So basically it mentioned about the problem 1, the outliers, and then problem 2, which has a strong correlation internally between different features. So you can see here we do some pairwise scatter plot to observe the kind of distribution, and then we include 3 columns in here. First column as a histogram, another one is box plot and a QQ plot. So you can observe a distribution in the histogram and to examine the outlier situation in the box plot, and also check on the QQ plot to see the actual and predictive, and also the skewness situation. So you can see in the box plot we have a lot of outliers. So in the next step we're going to deal with it. And also you can see here in the violin plot, this long line also indicate a strong situation we need to process on the outliers. And then as this heat map, you can see here a light colors indicate a very strong correlation between the features, which is not so good because we want to eliminate those non-redundant variables in the features. So we want to simplify the models to give a effective, simple, intuitive model selections. So that could be the plots we want to discuss a little bit. And in the next step in the coding, we do some checking on the skewness and encode the post type. And also we do a very strong data processing procedure, which is use the 2-key rule to remove the outliers, which means that the data points fall out of range, having the distance of the 2 interquartile range from the median are considered as abnormal, which is outlier. We want to remove those, and we double check on it by doing another box plot, so we can see there is no dots around this kind of range. And then after that, we want to do some validation, and also to take care of the correlation. So in this case, we do validation by split the training and test data set. We have a 80-20 ratios. 80% of data set are considered as a training data set to use it to predict, or to use it to fit the model, and use the model we fitted on those test data set to predict. So that could be ensuring the very strong cross-validation. And then we take care of the correlation and some outliers problem by doing standardization. This is meaning that we want to treat each features fairly by consider them into a same dimension or same standard to kind of weigh their importance in between each other. So what we're doing here is that to standardize them at a set score, so to avoid the situation made that somehow some features have a really large range in absolute value, and they're more they're having a larger absolute value, but they should not be considered as the most important feature. This could be maybe a wrong kind of decision rule. So we want to standardize them to treat them more fairly and projectively. So here we rank those features. You can see here in the tier 1, the most important feature could be shear weight, and in tier 2, the second most important one could be socket weight, and then the left one could be as considered as tier 3 important one. So in this diagram above, you can see there are two axes actually representing the actual data points and the predicted one. The ideal distribution or looks like should be a concentrated diagonal, while the more spread up or diffuse might suggest a low prediction power. I tested 8 models reviewing the machine learning procedures. The result could be quite interesting as well, which is more complex models aren't necessarily the better. The excessive regularization can be also very fatal. So first, take the multiple linear regression as an example. We have a few indicators to look at: the R-square, MSE, MAE, maximum error rate, and coefficient matrix. In short, R-square, the larger the better. MSE, MAE, maximum error rate, the smaller the better. So to dive into bias-variance trade-off, here is some first pair of example I want to discuss on. Which one is the ridge versus linear regression pair? The result could be nearly identical. The R-squared could be around 0.5 and MAE is around 1.61. These indicate a regularization of the ridge that smooths the coefficient from around 1.49 to 1.46. However, since our data was very clean and no severe multicollinearization issues due to the standardization, so ridge advantages in reducing variance is not that evident. This is an intuitive manifestation of bias-variance trade-off. It intentionally makes the coefficient estimate less precise to reduce the variance. However, in our dataset, variance was already very low after we doing turkey cleaning and standardization. So the advantages of reducing variance by ridge could be not so evident. And as another example, the lasso failure, we call it as a failure of the high bias or underfitting. R square is plummeted to 0.14 and MAE is surged around 2.28, with the maximum error rate reaching around 200%. And to examine the coefficient, the top 7 features were all compressed to 0, leaving only the last feature, shell weight, with a very trivial weight around 0.125. This is a classic example of underfitting. The alpha penalty was too strong, so forced the model to pretend only shell weight matters, while ignoring all those true predictive power of other features such as diameters, features. So excessive bias made the models over lazy to lose the ability to capture the data complexity. Another counterexample is kind of the failure of decision tree. This is a story about a high variance, or you call it as overfitting. The R-square is only around 0.2 and maximum error rate reach over 150%. A single decision tree attempt to create an overly complex rules to fit the noise in the training data, so resulting in an extremely poor generalization on the test data side. And this is a classical high variance problem. The model memorized and fit the training data so well, leading to a poor performance of unseen data in the test dataset. So overall, the selection of linear model is appropriate as there exists a biological linear relationship between the Ablone age and the shell thickness and weight. The linear regression achieved the optimal performance, which has an R-square around 0.5, and besides, there's no severe multicollinearity in the validation data. Less so underfit due to the excessive penalty of alpha around 0.5, and a single decision tree suffered from overfitting has R-square around only 0.2. The nonlinear models failed to outperform the linear models, so indicating an increasing dose complexity introduced variance weight without a benefit. So another one could be the real world implications. The first I want to mention is that to weight it to determine the age. The shell weight is the most crucial indicator, so the fishermen can simply use an electronic scale on their boats, so no need to cut and open the shells to count the growing rings. The second could be the simple formula delivers the accurate result. We can run the calculation using Excel spreadsheet, so no need to have expensive equipment or engineers. And also keep an eye on the extremes. The model occasionally making some big mistakes. The error rate around 80%. So especially to take an eye on the your young age and extremely old age. So that's the main content I want to discuss in this video. Thank you.